Okay, so hi everybody. I thought of calling it reviewing MIP star is equal to RE, the rise of the Phoenix, because I said I won't talk about it again, and here we talk about it again. But I think I had a chat with the guy and with Amnon Tashma, and actually a long chat, and we understood that the way I presented it wasn't the optimal way. And we thought of, after Guy's talk, a maybe better way of introducing the ideas that I talked about a bit, and also the ideas that I didn't have time to talk about in the previous 4 lectures I gave about this topic. I'm going to review things from Guy's talk and then to connect them to the quantum setting in such a way that maybe now things will be clearer. Hopefully, things will be here clearer. So actually what I'm going to do, and I also said it in my last lecture, last 2 lectures, I think, is that I'm not actually going to show you the protocol of the proof of what I call the recompression theorem. We showed that modulo this theorem called recompression theorem, MIP star is equal to RE. So I'm not going to actually show you the way of proving the recompression theorem. I'm going to show you something that enables you to prove a weaker statement that only NIXP is contained in MIP star, which is a paper that was published about a year before the MIP star is equal to RE. But the main ideas that enable one to prove the recompression theorem also appear here. So it's just an easier way, like it's easier to introduce this proof than the recompression theorem. Okay, so just for ease of presentation. So I want to recall like what Guy did. So Guy showed us that actually, if you want to show that, just a moment, maybe I'll do like that. If you show that 3-sat, no, I need to stop the share and reshare because this always stop working fast enough. Okay, hopefully now it will be okay. Okay, so if you show that 3-sat is in what a guy called a multi-loadeg poly proof with here he took 1 over poly, okay, and I'll explain the notation. And we have now polynomially many polynomials, and we have only 1 round. So he said that if the succinct 3-sat problem can be solved using access to polynomially many low-degree polynomials, and the completeness soundness gap is 1 over some polynomial in the size of the instance, then we can deduce, he showed the reduction that actually succinct 3-sat is in what we called, and this is an easier thing to understand, multi-prover interruptive proofs with completeness soundness gap of 1/2 with 2 players and 1 round. Okay, so this was his first talk. He showed this reduction, and he used parallel repetition, and he used the low-degree test, and many tools that I'm also going to talk a bit about today. And then he showed us how to use arithmetization of the formula, of the Boolean formula that we were given, the instance of the succinct 3-sat that we use, and the combinatorial Nullstellensatz to actually solve the problem. So let me remind you what he actually did. He wanted access to this assignment function. So this, the A hat was the arithmetization of the correct assignment to the Boolean formula that is generated by the circuit. Okay, and the combinatorial Nullstellensatz, you need also polynomials, as many polynomials as variables to check that actually this polynomial is the identity on some cube, right? So the interaction between the verifier and the polynomials is one of two options in Guy's protocol, okay? Either the verifier sends to all of the polynomials the same point in this vector space, or maybe this will work. Oh, wow, it works. Okay, so either he sends a single point, but to all of the polynomials in this vector space, or he sends a point in this vector space to all of the polynomials. Maybe these are other polynomials. When he's using 2, the G's are not the same for 1 and 2, okay? But there are these G's maybe different for 1 and 2. And when he is actually asking 1, he's checking this condition, the fact that if you take the arithmetization of f and you compose it with doing nothing to I, alpha, beta, and gamma, but evaluating a hat on alpha, evaluating a hat on beta, and evaluating an a hat on gamma, and you take -1, this should be 0 on the cube, on 0, 1 to the n, or something like that, to the, not n, m plus 3l, right? This is the correct number in this case. And otherwise, if he does the second test, he needs to check that this polynomial is of low degree and is 0 on the cube.
Yeah, actually, this was at the end, and maybe I didn't explain it well enough. So let me just say that we showed 2 tests. One is to test that the assignment is a 0-1 assignment because it's just given as a huge polynomial, and
which is this 2 thingy.
Right, and another test was assuming A is a 0-1 assignment to check that it satisfies the formula that F represents. So this is number 1 here. What I didn't...
And actually you need access to 3 points in A in this number 1, and we a bit...
Yeah, let's forget about that for now. But even these 2 checks, each of them requires to access A. And we only get to ask A 1 question. So we cannot do both tests at the same time. What we actually do is we pick one of them at random and apply only that test.
Yeah. So and we are okay with something, guys, just saying compose test, like flip a coin, either do this test or do the other test. Like this is, we are okay with such things.
And the point is that if the players want to succeed well in this combined test, in this, in order to succeed with very high probability, they have to play with a strategy that wins well both for test number 1 and for test number 2. And if they want to do that, they really need to answer with respect to some polynomial A that is 0, 1 valued on the Boolean assignments, and also that polynomial should satisfy F. If it only satisfies one of those things, they will fail whenever that test is selected.
Okay, great. Okay, so we now recalled what Guy did in his previous 2 talks, but I want to compress back. Guy mentioned that actually knowing this implies that you know it for only 2 players. So I want to compress back this game to a 2-player game. And okay, before I do that, I want to just mention that notice that the only thing that I ask the polynomials are points in some vector space. Okay, so my questions are just points in some vector space. And this will be important because you can recall, and I will do it also later, that I had these self-testing gadgets that enabled me to force the provers to measure some point. So this enables me to force them to measure a question in this kind of a protocol. But I'll go back to it later. So let me just say that using Guy's reductions, you can actually, he didn't explain what the low degree test is doing. So he did mention what is the idea. You, instead of just asking a single point, you ask for d+2 points, and then you check whether the interpolation of the d+1 points is consistent with the d+2 point, right? And this checks whether he uses a low degree polynomial. So he said something about that, but I want to frame it in a different way. There is a point player, which actually gives me the answers to all of these questions. Okay? So the point player actually needs to give me the answer to a hat, all the G's, the number of times that I want answers from a hat, and so on. And the subspace player, okay, and notice that we ask the same point to all players, so this is good for us. And the subspace player just gets some affine space that contains either the point I alpha beta gamma or the point alpha. And the dimension of this affine space depends on what we actually want to prove and use. And in our case, you can think of just taking either a two-dimensional space or a three-dimensional space or a one-dimensional space, okay? So it depends, but we don't need anything larger than 3 dimensions. And we check consistency. What does it mean? It means that actually, if we send here I, okay, so I need now some color. If I send here the I alpha beta gamma, I expect to get back a hat of I, okay, a hat of alpha, a hat of beta, a hat of gamma, and all the G's of I alpha, beta, and gamma, right? This is what I expect the point player to answer, to give me answers to. But I expect the subspace player to give me some actual polynomial, G, Gi, or Gj maybe, because I have I, Gj's, maybe with tilde and not with hat, Gj tilde, actual polynomials, Gj tilde, and a hat tilde, I don't know, that are defined only on some line, for example, that goes through I alpha, beta, and gamma. And the point is that I use the same line. For all of these polynomials, I use the same line. Okay? Or either I use the same line, or I use the same subspace of dimension 2, or I use the same subspace of dimension 3. So for example, to use actually 3 points, I'll send both a subspace of dimension 3. But if I only use this alpha, I'll send the other player a line that passes through the point. Okay, was that clear? Like what have I changed? I compressed everything to 2 players.
I could do with a little bit more explanation.
Yeah, okay.
No, I understand. No, the thing, okay. What you explained was completely clear. What the guy explained was also clear. What's not so clear is that you're saying now that what you're giving us is somehow a cheaper version of what Guy said, which is still enough. I mean, am I getting this correctly?
Yeah, but I think even Guy actually showed this kind of reduction, modulo the fact that he didn't talk
well,
much about the low degree test.
What I showed was a little different, because I could have said something like this, but this is not what I said. No, I didn't use just a point question and a line question. I had a point question and then d+1 other point questions to to D+1 other provers.
No, these were the same points.
What?
But these were the same points.
No, I'm talking about the low degree test.
The low degree test. Okay.
I didn't do a point versus line in this sense that you're showing.
Yeah, right.
So it's a little different.
What I mean, I was able to understand either one of you individually. I think you're trying to say that, and the stories, of course, bear resemblance. But you're trying to say that it is, in fact, the same story. That I'm not 100% sure I understand. Perhaps it's not so important. Perhaps we can stay with what you're telling us.
No, not. I think it is important.
So please explain.
Guy said that every game with multiple players, you can compress to a 2-player game by just asking one of, this is some kind of oracularization. You ask one of the players, you have only 2 players now. You ask one of them the answers to all of the questions that you would have asked all the other players. And then the other player needs to, you ask randomly to answer as the ith player out of these original players. And Guy said that you pay some soundness constant here, but it's okay. It's still in the polynomial regime, so we can do parallel.
This is the passage from 1/2 to 1 over poly.
Maybe, yeah.
In this, you will. I mean, if you started with 1/2, you will go to a gap of only 1 over poly. Actually, we started with the lower gap, but still, you pay a price of multiplying the gap or dividing the gap by a polynomial number.
Yeah, but doing it twice is again a polynomial. So we are, even if we started from a small 1 over polynomial gap, we still are in the 1 over polynomial gap. Okay. And then we can use parallel repetition. So this protocol that I'm showing here, this game that I'm actually stating here, is still, it's not in the M loaded poly P 1 over poly, it's in MIP 1 over poly, but now only with 2 players and 1 round. If I want to make it to MIP with 1/2, I need to do parallel repetition. But at this point, I don't want to do parallel repetition because we will need to do the parallel repetition to our protocol in the quantum case. So for at least for now, this is just this game is in MIP 1 over poly 2-1. And the questions are just of the form questions are points and at most 3-dimensional subspaces. So maybe I send lines, maybe I send planes, and maybe I send 3-dimensional subspaces. Either one is good for me.
So
okay.
just to maybe follow up on Nati's question and on what Guy said, basically this is a different way of showing. So Guy walked in one way of actually showing a multi-prover game and then making it a two-prover game by basically putting all the questions to all the provers in one prover, and then a sort of a verification prover that just asks a single coordinate. And this is a different way of doing it by basically point and a subspace, what you're now showing? With the same, and is it with the same parameters as what Guy showed?
Not exactly the case, because actually Guy talked about access to polynomials. And you should ask yourself, what does it mean to access a polynomial? To access a polynomial means that you do some kind of a point versus line or point versus plane or point versus 3-dimensional subspace test. This actually, so he said it by just saying I'm measuring on over D+2 points on the same line. So actually, you can interpret what Guy did as a point versus line test. Okay, you can interpret what he did as this test. I'm claiming that there is a bit more general test, just checking instead a point versus a line, a point versus a plane that contains this point, or a point versus some three-dimensional subspace.
And do you gain anything by that? Like, what is the advantage of that, or just generalization?
If I want to measure the same polynomial at 3 different points, I need higher dimensional spaces in my setting. I want the same polynomial at few points. So Guy mentioned that you can actually just think of the same polynomials as 3 different polynomials, and sometimes just check consistency between these polynomials. This is also possible. Maybe Guy, you want to elaborate on this point? Maybe we'll do it.
Yeah, okay. You are talking about things that I actually never got to say. I actually put it under the rug.
So maybe say something about it, and I'll try to move from that.
So in the test that A satisfies the formula that F represents, I actually needed to evaluate I had to evaluate the polynomial A at 3 different random points. Right, it was choose alpha, choose beta, and choose gamma randomly, and then evaluate A at alpha, A at beta, A at gamma, and then evaluate the formula F. Here's like it's written in item 1 in the test. But this is one round, and all the questions that I'm allowed to ask A is, I can send A an X, and the A polynomial will give me A of X. How can I evaluate A at 3 different points in one round? And the way that one can do it is to have 3 polynomials for A. So instead of having just one A, to have 3 A's, and then send alpha to the first, beta to the second, and gamma to the third. Now, the only problem is that now we have to verify that these are the same polynomials, because these all need to be the evaluation of A at a certain point. And the solution for that is to do everything that we said with probability 1/2. And with probability 1/2, send the same alpha to the 3 A's. Evaluate A1 at alpha, A2 at alpha, and A3 at alpha. The provers don't know that I'm doing that. They get a random element in each variation. And then when I evaluate all these A's at alpha, I can just check that they're all the same. So this is one way to, and this can be generalized. So I can read, even in one round, I can read several evaluation of the same polynomial if I need it. But there is a different way, which is in some sense much stronger, which is to ask because this, what you're suggesting here, what Michael is suggesting here, doesn't need to even assume that I get evaluations of polynomials. In what I showed, I assumed that I get evaluations of polynomials, and then I said that after that, you need to add the low degree test. This does everything at once. You ask for values at a certain point. You ask evaluations at several points. You ask one prover for that. And then the other prover, you ask for a subspace, or not for a subspace. You send them in a subspace and you get a polynomial over this subspace. And you check consistency, that the polynomial over the subspace, when evaluated on the points, gives the same evaluations as you get from the first prover. And now you use a theorem that's actually not very simple, that shows that in order to succeed in this line of questioning, the provers really need to answer according to some low degree polynomials. So that's the point versus space test. So this was proven, the fact that the test works was proved. Okay, I will not go into the historical details. You can continue, Michal.
Okay, thank you, Guy. More questions? I think this is an important point. So now okay, the reason that I'm showing it that way is because now the questions are I need just to define a point and define a subspace and send them appropriately to the players. And now you can at least believe me that modulo the things that Guy showed and said right now, this thing actually solves a succinct 3-sat.
Guy, just to make sure, what you didn't tell is BLR, that or more advanced?
No, this is more advanced than
more advanced.
BLR.
You need to do induction on the, it's a more advanced thing. It's low,
and also it's a different test. BLR is, BLR is very simple. You want to verify that a function is linear, and you evaluate it at x and at y and at x plus y, and that's very simple. Here the test is completely different. You evaluate a function at several points, and then you ask a prover to give you, or then you evaluate a different function that whose input is a subspace and whose output is a low degree polynomial over this subspace. So you evaluate this and you check consistency. It's a totally different test.
But there is no name for it, right? It's not point versus subspace. I looked for it. There's
several points.
I think
is there a name?
What?
Is there a name for it?
I think the basic version is called the point versus plane.
But yeah, but okay.
This is it first by point versus plane, but if you want 3 points, then you need subspace. That's all.
Okay.
Yeah. The core is to prove that point versus plane works, and the other things you get by reduction.
Yeah, I want to say a small thing about this point. Not the point, but the point that we mentioned, that actually in the MIP star is equal to RE. Now I'm going to talk about like the general point versus subspace, and this will be enough for my introduction. Actually, they need a bit more convoluted point versus lines and not uniformly choosing the lines. And it's a bit more complicated, but still the ideas of what I'm going to show work. And in our head, I'm just choosing like 2-dimensional subspaces. And from now on, I need to somehow define a point to one player and the 2-dimensional subspace to the other. This is the questions that I send. Okay? Great. So now I want to talk about succinct 3-sat. So my goal is to show today and probably next week, because we want to actually understand everything, that MIP star contains, okay, so NEEXP is contained in MIP star. And for that end, I need just to show you that succinct 3-sat is inside MIP star. Okay, and this is MIP star 2-1 with completeness soundness gap of 1/2 with the Guy's notation. Okay, so let me explain what is succinct 3-sat. Okay, so we know that succinct 3-sat is just getting a Boolean formula, as in Guy's talk. And this Boolean formula defines somehow, at least in some cases, not in every case, but at least in some cases, an instance of a 3-sat. Okay, and we want to understand whether this 3-sat is satisfiable or not. This was the instance in the succinct 3-sat problem. Now, the input in the succinct 3-sat problem was a Boolean formula. Now, what do we have? What information do we have in a Boolean formula? We have, okay, so maybe I'll not ask it. I will not actually ask it. So I'll just say that you have some inputs, right? And you have gates. And okay, so inputs is easy. You just say how many inputs you have. And then gates are just of one of 6 types, okay? So now I'm claiming that the inputs are also gates. So I'm going to put the inputs as, Guy said that I don't want to think of them as gates, but now I do, just for the characterization of how a circuit can define a Boolean formula. So a gate can either be an input and then it doesn't have any inputs, doesn't have any inputs. It is just an input by itself. Okay, it can be a negation, and then it has one input. It can be an AND, or it can be an OR, and then it has 2 inputs. And it can be a true or a false. Okay, so I also add the possibility of just adding a true or a false to something. I'm not sure that we actually even need it, but this is usually done. Okay, and here we have 0 inputs again. And now, how do I define a circuit that is exponentially larger? How do I define a Boolean formula which is exponentially larger than a circuit that defines it? I do the following. Okay, so for any I, now I have a circuit that has n inputs. Okay, so this is this n here. And the circuit is doing the following. It's very similar to Guy's Boolean formula. And again, for any I, it is doing the following. It outputs a number between 1 and 6, okay? The number between 1 and 6 defines whether this I is an input, a no gate, an AND gate, an OR gate, a true or a false. Okay? This is what the first output of the circuit means. And after that, it tells me where are the inputs to this gate. Okay? So if it has 0 inputs, the alpha and beta that he gives me are just 2 empty sets. Okay, there is no input to an input, and there is no input to a true gate, and there is no input to a false gate. But if it is an OR gate, you need to tell me an OR of what, right? So if it's the OR of something, you need to tell me something like, okay, so if n is 4, let's give an example. If the input was 0, 1, 1, 1, so for example, it can be a no, so it will be a 2. The answer will be, maybe I'll do it with orange. 0, 1, 1, 1. This is the input. The output will be a 2, meaning this is a no gate, and it is the no gate of 0, 0, 0, 1. Okay, and empty, because no gate has only one input. But if it is an AND gate, so I can do what is 1, 1, 1, 0. It is an AND gate. It's 3 of 1, 0, 0, 1 and 0, 0, 1, 0. Okay, and you agree with me that if I just calculate for any binary string of length n, I check what this circuit tells me, it outputs an exponentially large circuit. Okay, so this is a succinct way of defining a circuit. Any questions about this point?
How many initial entries are there?
I didn't understand what you just did. Sorry.
Okay, I tried to define a succinct way of defining a circuit. So how do you do it? The point is that you start with n inputs, you do the same as with Guy's thing. You take two of them and you join them and you calculate something, okay? But at the end, you don't have only one input, one output of 0 or 1. You have many outputs. How do the outputs look like? You have the first output, which is a number between 1 and 6.
Mm-hmm.
Okay? And then two outputs that are either binary of length n or an empty set.
Mm.
These are the possible outputs. How do I interpret these outputs? I interpret them as if I got a 2, this is a no gate, and then it is the no of the first input here, and the second one must be an empty function because there is no other input to a no.
I understand. The four got me confused. I thought the 4 was inherent to the. I understand. It's length n.
Yeah,
N equals
yeah,
4.
you're right.
This is
I
what
chose n is equal to 4 as an example. It's 0, 1 to the length n. This is the length of the input for the circuit. And the point is that now how many gates are in the circuit? There are exponentially many gates. This is the point. So this is an exponential.
Exponentially n.
Right. There are 2 to the n gates. At least
you want
I find it, they are exactly 2 to the n gates, but I can add just, false and true gates that are doing nothing, and then I can manipulate a bit this size, right?
In succinct 3-sat, we had a formula of small size that described a formula of much larger size. This is similar, except in succinct 3-sat, the small formula had to describe a 3CNF. And here, the small formula describes something more general. It describes a general other bigger formula. So you have to do it, you have to do a little more. But now that you did it, you can, if you want, define succinct 3-sat and succinct, whatever, any number of succincts that you want, and it's the same thing. You get a circuit that describes a circuit that describes a circuit that describes something.
So how come we never really have to go deeper in this hierarchy?
We do if you want to define non-deterministic triple exponential time and non-deterministic quadruple exponential time.
Do we? I mean, do we need it for this proof or?
In our, no. We don't need it because the compression theorem that I described at my 4th or 5th lecture solves it. And there is a way to circumvent this induction. You don't actually need to show that NICSP and then n with 3 e's and then n with 4 e's and n with 5 e's. I'm just giving you the flavor of the ideas in the proof. And then at some point we'll explain when do you actually need to do more to prove the recompression theorem. Anyway, this is a succinct way of defining a circuit. And as Guy said, now I can define succinct 3-sat by just saying the input is a circuit that defines a Boolean formula that defines a 3-sat. And we want to ask whether this 3-sat that is now doubly exponentially larger than the original input is satisfiable. So I'll just explain what I called previously the big protocol, and then we'll take a break, okay? So you are given, what is an instance? So an instance in 3-sat, in succinct, okay. Instance in a succinct 3-sat is some C that defines some Boolean formula. So I'm keeping to Guy's definitions, a Boolean formula F. Okay, so this C is a succinct version of F. So what is the big protocol? The big protocol is quite stupid, but it is a protocol for NEEXP. And it's doing the following. It unravels the definition of f. So it just calculates for every input 0, 1 to the n, what is the 0, 1, like what is the gate at this point and which are the previous gates that it depends on. It just calculates this, this Boolean formula. Now this Boolean formula is of what size?
Exponential.
This is exponential size. Exponentially sized, I don't know. It's exponential. Okay, now I just use guys, not guys, but my, okay, this protocol, which is, I deduced from guys' 2 lectures, this protocol, and I'm just applying this protocol on the exponentially large Boolean formula. Okay? Now, the size of questions and answers in this protocol was polynomial previously. What is the question and answer length now?
Exponential.
Now it's exponential. And the point is, even just understanding what is the circuit, so my pre-processing, even before I send anything to the players, I already consumed exponentially long time, right? Just writing down F took me exponential time. So even before I send any question, I'm using exponential time. And also to check whether the answers are correct takes me exponential time, right? So everything here is exponential. The length of the questions, the length of the answers, and the time that I need both to generate questions and to check the answers, all of them are exponential. The goal of the reduction showing that NIXP is in MIP star is by first making this and this polynomial. And this is a purely quantum thing. This is what I called question reduction. And this cannot be done in the classical setting, okay? But there is also this part that I didn't talk about at all, and hopefully, I don't believe that I will be able to talk about it today, but next week I will talk about it. This is answer reduction. And this uses classical PCP. Okay, so you need
Michael,
to
reducing. You didn't.
Can
you want to reduce.
Sorry, Michael, can you say that this could have been done classically if the provers had a trusted random source that the verifier can sort of trust?
Trusted in the sense, yeah, this is okay. If I replace the quantumness by the fact that actually I can, some random resource, which is infinite in the sense that it can send unboundedly many random bits to the both players, it can replace the quantumness of this part, right? This is correct.
Well, you will have to somehow verify that they act according to, that they do their computations using their random, the random source that you gave them.
Okay, I need to think about it. Anyway, this cannot be done classically because we know that NIXP is not contained in MIP without star, right? So at least maybe I said something wrong a minute ago, but it is true that this is a quantum phenomenon, this part, the fact that you can reduce the size of the questions and the pre-processing before you send the questions. Okay, so this is the more quantum part. And my claim is that the answer reduction is a more classical thing. So this is just PCP results. And hopefully when we'll get there, you will help me with it because it is black magic to me, all these PCP results. So
just
a fruitful discussion there. Okay?
Yeah, but yeah, so you just never actually said that you're going to reduce the answer and the time length to polynomial.
Yeah, so I'm going to reduce everything here to polynomial first, the question, the purple things, and then the green things. And I do it in order. So first the question part, then the answer part, and the answer is more classical. The question is more quantum.
Michael?
Yes. Okay, so we'll take now a break of 10 minutes. So questions during the break.
Yeah, I understood your translation of taking the circuit for a succinct FreeSat instance and making it a succinct, like coding it using this function C you define. But if I understand correctly, for this to be a C instance of succinct FreeSat, you need to require that this function C itself can be written as a polynomial circuit, right?
Yeah, it is. It is given me as a circuit of polynomial size. It has only polynomially many gates. Actually, you should think, Alon, you should think of the circuit itself as the input. So saying that is polynomial is trivial. You get an input, the input is a circuit. The size of this circuit is what I call N.
I think what Alon, maybe I'm wrong, but I think what Alon is asking is that, you know, this formula...
Need a polynomial description of it, no?
Yeah.
This formula is, C is just a function with
Yes, so generally,
Okay,
how do you write it down?
Almost all formulas will not have a succinct description. That's true.
Wait, Guy, it depends what is the input. If the input is the number N that I written here, the N on the power of the 0, 1, you are correct. But if the input is the size of the circuit C that I got, this is not true. Like if I got a circuit of size of like the input is just the size of the circuit, so it takes only a polynomial in the size of the circuit time to calculate a circuit, right? It has polynomially many gates.
Alon's problem is different, so let me just try to say what I want to say, and if that answers Alon's questions, then good. Otherwise, we'll try again. So, Alon, it's not that every formula, every exponential size formula, you can describe by a polynomial size circuit. That's, of course, very far from true. What turns out to be true is that even if you only restrict yourself to the set of formulas that do have to the set of exponential size formulas that do have a polynomial size description, these formulas, when they are described succinctly, are complete in double exponential time. So it's enough for you to be able to describe those, which you can.
Mm-hmm. So I should, the bottom line is, however you want to treat your, whether it's Michael treating the size of C as the input or you want something else as the size of input, I should think of C as a circuit, right? And the size of this circuit as
C is a circuit. And then
okay, I think
you have an input which is a circuit of size N, because we define N to be the size of the circuit.
But your remark is that only looking at polynomially sized circuits, describing a succinct FreeSat problem, this is complete.
This is complete in double exponential time, yes. So it's enough to show how to solve these questions in MIP star, and you've proven that NIXP is in an MIP star.
By the way, the circuit's value, I mean, the values of C are not just bits, so it's like you need, it can be tuples, it doesn't matter.
Not just one circuit, but maybe 6 circuits or whatever, however many you need. Each gives you 1 bit of the output.
Okay.
That doesn't, that's,
Yeah, I maybe.
I think I understood both of you now.
Okay, good.
Yeah.
Can we go back to the original protocol of S FreeSat problem that the talk began with? So you have these 2 conditions that you have to verify.
Yeah.
So the verifier decides which one wants to verify.
Yeah, he flips the coin before the test and just decides that he uses.
And then sends to the players the set of questions that it needs. And the players can realize what condition the verifier wants to verify because of the question.
So you can do it in a way that they cannot.
It's
You
just
can-
that
you
the
can
questions
always-
are always to each like polynomial or each prover. If you look at what question is sent to them, it's always just a uniformly random point in the domain of the polynomial.
Yeah, so
I mean,
because of
it's not a law
because
of
of the-
nature. It's just what happens in these particular tests.
Guy, because this is because of what you did with the 3 A's. So actually, there is not
Yes.
only one A here. You need to duplicate it 3 times, and then you send alpha to one of them, beta to gamma, to beta to one of them, gamma to one of them, or alpha to all of them. But they only get a point, so they don't need to know whether you're doing 1 or 2. And you don't care about the other polynomials. They are different. So the G's, and actually there are H's here, right? There are G's and there are H's. And there are not the same amount. Like there are maybe m plus 3l H's and LG's. And then you check, in the 2 case, you check with the G1 to GL, and in the 1 case, you check with the H1 to HL. But you can always send them questions and you don't care. You only use the answers from the one you actually check now.
Yeah, so in a way, even if hidden, you still use some, you sometimes just play the game in order to verify that they are honest.
Yeah.
With their answers. Like, yeah, thanks.
מיכאל, מה היה הדיון בנוגע לשאלתו של אלון, ומה התשובה?
אלון שאל,
English, past
okay,
English.
so Alon asked whether, like, the relationship between the fact that your circuit that defines the succinct circuit is only polynomial, so it defines only polynomially many exponentially long, large.
It's a small set in the
yeah, but it is still the complete problem for non-deterministic exponential time, and the succinct thingy is the complete problem for the doubly non-deterministic double exponential time. So this was the discussion.
Is this completeness easy, obvious?
It's the same Cook-Levin theorem. Maybe, I don't know. There is the reduction in Papa Dimitriou's paper, I think, like it's a classical book, right? And it handles all the succinct, and so on.
It's not very succinct, though.
What's involved? Guy,
Huh?
what's involved in proving it?
What, the succinct thing? If I remember correctly, nothing special. It's just, you know, you go over the Cook-Levin reduction and you verify that the construction is simple enough that you can, in log space, decide whether a certain gate appears somewhere or not.
Okay.
Okay, so if you're here, it would be nice to see your faces. So I'll know whether to resume or not. Okay, I'll wait 2 more minutes.
Oh, I just realized that, Nati, that you asked me what's involved because I said that it wasn't very succinct. But I just said it because it sounded nice. It's actually, no, it's not very verbose or anything.
Okay, I think I will resume. So we had this big protocol, which solves an instance of succinct 3-sat, but with questions and answers that are exponentially long and clearly exponentially time of complexity time to generate the questions and to verify the answers. So as I said, I want to first explain how can you reduce the size of the questions. And this is, and now it will be important, the fact that the way that the game is, the questions in the game are just sampling points and sampling subspaces out of some vector space, finite vector space. Okay, so how do we do it? We want to sample points and subspaces of some f2 to the t. So now I'm taking my field to be of characteristic 2, okay, to the m. And it is allowed because the only thing Guy used is the size of the field. So we can choose t to be large enough such that the size of this field is good enough for all of the properties that the guy needed. Okay, this is what we want. So to that end, I need this notion of self-testing. So recall how we defined self-testing. It was the following. So a game is a self-test if it has only one winning strategy up to isometry. So recall that the strategy is a sequence of POVMs. So what is a strategy? Yes, it's for any question X that we had, there exists a POVM A, X, A, where A, small a comes from the answers, the possible answers of player 1, and for any X, okay, so this is IA, this is no, it was OA, I think in my outputs. Okay, so inputs and outputs. And for every Y in IB, there exists a POVM B, A, Y, for any B, Y, B, for B's in the possible outputs of B, and so on. So this was a strategy. And the point is that such a strategy is just a sequence of matrices, and these matrices and the state, okay, so we had also a psi that lives in some Hilbert space of A, tensor Hilbert space of B, right? And the point that is that up to isometry, you can embed this HA tensor HB in some larger tensor product of two Hilbert spaces, such that psi is a specific state, and the POVMs under this isometry just become specific matrices that act in a specific way on some part of the state, and there is some junk part of the state that we do nothing on, the auxiliary part of the state that we do nothing on it. Okay, so this was self-testing. Okay, this was a very quantum thing, and we saw that CHSH is such a game. So we saw that CHSH is such a game. And the point was that in CHSH, you know that to win CHSH, the players need to share a single EPR pair, right? They need to share this 1, 0, tensor 1, 0 plus 0, 1, 0, 1, tensor 0, 1 divided by square root of 2. This is the psi that they actually use. And they need to measure the state. One of them needs to measure the state either with respect to what we call the X basis, the measurement that comes from the matrix 1 as 1, 0. Okay, so this is not X, this is Z. So one of them needs to either measure according to the X, which is 0, 1, 1, 0. This is just the unitary. We defined somehow a unitary with respect to a projective valued measure, and this X is the unitary that is defined using this projective valued measure, or it uses Z, which is 1, 0, 0, minus 1. Okay, so we saw this kind of result when we talked about the CHSH game a few talks ago. And we said even a stronger statement that actually this is not just a self-test. There is not only one strategy that wins this game up to isometry. Every strategy that almost wins this game, in the sense that the probability to win is 1 minus epsilon, is some function of epsilon close to this strategy. Again, there is some isometry and there is some distance and the correct notion of distance such that this strategy is close in this distance to the perfect strategy, the unique perfect strategy. Okay, so this was self-testing. I just recalled what does it mean. And I want to give another example. So we had this CHSH game, but it is the problem with the CHSH game, if you remember that the best strategy wins 1/2 plus 1/2 square root of 2 of the times. Right? It is not perfect complete. It doesn't have, you don't always win the CHSH game, even if you use the best strategy. Now, the good thing about the Magic Square game is that it actually has a quantum strategy that always wins, that can never lose. And I'll explain what the game is, and then I'll say something about the strategy. Okay, so the game is the following. You have a 3x3 grid. I'm sorry that I draw very poorly. And an instance of a round in this game is composed by one of the following things. So I'm writing here, well, maybe X1 is not good. A11, A12, A13, A21, A22, A23, A31, A32, and A33. And I asked, there is a line player, again, and the point player. And at the beginning of the game, I just randomly choose which one of the players is the line player and which one of the players is the point player. And to the point player, I just send a ij for some I and j between 3 and 1. And to the line player, I either send a ri or cj, meaning if I'm sending A12, okay, so I sent, orange is my example color, examples color. So if I send A12 to the point player, I either send the first row R1 to the line player, or I send a column 2 to the line player. So and the answer should be, so the point player just needs to answer with a single bit. So I'll move back to black. The point player needs to answer with a single bit. And the line player needs to answer with a triplet of bits. And I think it's quite clear how do I interpret their answers. So when I ask A12 to the point player, I'm asking the point player to give me some value here. So either a 0 or a 1. Okay, and when I'm asking the line player to answer what is the triplet, it's just how do you fill up this row or this column. So if the line player answered 0, 1, 1, it means that he means to R1, he means that A11 is equal to 0, A12 is equal to 1, and A13 is equal to 1. Okay, so I just explained what are the questions and what are the answers. Now I need to explain when do they win. So they win if they do two things. So to win, they need to be consistent. So what does it mean to be consistent? If I'm asking the line player for row number 1 and the point player for A12, the output that is related to A12 out of the line player needs to agree with what the point player sent me. Okay, so they need to be consistent with one another. This is my first condition. And my second condition is some arithmetic condition on the output of the line player. So this is just a restriction on the outputs of the line player. I want the sum mod 2 of the lines. Okay, so all the lines need to sum up to 0 mod 2.
All the rows.
All the rows, all the rows need to sum up to 0 mod 2. And all the columns need to sum up to 1 mod 2. Okay, so this is quite a straightforward game. So you can think of it as a linear system of equations. So we have 6 equations over the field with 2 elements defined by the rows and by the columns. And at each round, I send to one of the players an equation. The line player gets an equation, and the point player gets some variable that appears in this equation, and the output of the variable and in the equation and of the point player need to be consistent, and the equation needs to be satisfied. So this is the kind of games that come out of linear systems, just regular systems of equations, linear system of equations. Any questions about the definition of the magic square game? Okay, great. So first of all, there is no, okay, so facts. There is no classical strategy that always wins. Okay, so why is this true?
Because the equations are inconsistent.
Yeah, exactly. So we saw that the maximum value of a game is achieved by a deterministic strategy. And the deterministic strategy is just choosing some inputs to the linear system of equations and checking whether it's satisfied or not. And since it cannot be satisfied, they can never win perfectly using a classical strategy. Great. Okay, so this is this case, but there exists a quantum, a perfect. Perfect means value 1, quantum strategy.
So it's also finite dimensional.
Yeah, when I'm saying quantum, it means finite dimensional. So actually, they only need to share 2 EPR states. Okay, this is the what they need. And I'm actually going to write down, okay, so recall the X was 0, 1, 1, 0, and the Z was 1, 0, 0, minus 1. And when I'm saying that they measure according to this thing, they take the basis that diagonalize these matrices and with probability that is proportional to the projection on the eigenspace of a specific eigenvalue squared, they choose this eigenvalue, okay? So here they don't choose zeros and ones, they choose ones and minus ones, but clearly you can replace all the pluses by products, all the zeros by ones, and all the ones by minus ones, and you get a similar game, right? Just check whether the product is 1 or minus 1, instead checking the sum is 0 mod 2 or 1 mod 2. Okay, so there exists a quantum strategy that somehow uses these matrices. So I'm just going to tell you how the point player is measuring each of the, okay, so I'm going to add a page. Yeah. I'm going to tell you how each of the players are measuring how the point player is measuring each of the cells in this this magic square. Okay, so my matrices, so the Hilbert space is both Hilbert space. So for Alice and for Bob, I think it needs to be C to the 4. Yeah. C to the 4, not C to the 16 or something, great. But it means that the state that we use actually lives in C to the 16, right? This is what it means. Great. So what do they put inside the boxes? So hopefully I will be able to write it down. So one of them is taking the Kronecker tensor product of X and I. Here they take I tensor product with X, and here they take X tensor product with X. And what is the multiplication of these 3 matrices? So X squared is just the identity, right? So when you multiply all of these matrices, you just get the identity tensor the identity, which is the identity. But this means that no matter what they measure, okay? So the way that they check what is their answer here is just doing some inner product of psi and X tensor I on psi with psi and so on, right? This is the kind of calculation. They don't do it with X, they do it with the projections on the eigenspaces, but this is the kind of calculations that they do. But at the end, you can check that the point is that no matter what the calculation gives you, you can take the sums and minuses and all of that. And if you get here the identity, tensor the identity, they will always answer with the +1. So the product of all their answer will always be +1 because all of these matrices commute and their product is I tensor I. Okay, so next thing, we just take I tensor Z, Z tensor I, and Z tensor Z. This is the same thing. Instead of taking the X's, we took the Z's and we did the same, but we want that these 2 matrices commute. So you see, instead of taking Z tensor I took I tensor Z because I want these 2 matrices to commute. I did the same here and I did the same here. So you can check, it's not that hard to check that X tensor X commutes with Z tensor Z. We actually used that when we calculated the eigenfunctions, the fact that the EPR pair is the only eigenfunction of both X tensor X and Z tensor Z. It came out because they commute. Okay, and lastly, what do we need? So here, I maybe need some notes. I'm sorry that okay, so you would expect something like here xz tensor zx.
X and Z anti-commute? I don't remember.
X and Z anti-commute, yes.
So maybe you want something of the form Z tensor X in the left, bottom left entry.
Z tensor X and
So
X
that
tensor Z you want here. I think, no, but this now, yeah, this, no, this doesn't work, right? Because now I want them to commute with both of these matrices, but I don't want them. Maybe I just want minus X tensor Z here and minus Z tensor X. This probably works. Minus Z tensor X. Now these two are commuting. All of the columns here are commuting. All the columns here are commuting, right? And these two are commuting. You can check that these two are commuting, but here I want to take something like XZ tensor ZX, or maybe plus minus of this thing. Okay, so it's a problem that I haven't prepared this last line, but you need to take either the plus or the minus of this matrix together with these two matrices, and then you get what you want. And what is the state that they need to share? And then we can just check, okay, maybe we do multiply all the elements of this column. Let's check column number 1. What is X tensor I times I tensor Z times minus X tensor Z, right? So this is minus X tensor Z squared, right? But this is just minus X squared tensor Z squared, which is just minus the identity tensor the identity. So again, the fact that we got minus the identity tensor the identity exactly means that no matter, okay, so it exactly means that if they measure their what is on the columns, their answer will be always -1. The product of their answers, the fact that the product of these matrices is always minus the identity, means that the product of their answers will always be -1. And the psi that they actually need to use, okay, and this is because of consistency. So not because of the equation will be satisfied even with other states. But you need this specific state for them to be consistent with one another. The fact that the point player is consistent with the line player, they need to take EPR twice. Okay, so this is just 1, 0, tensor 1, 0, plus 0, 1, tensor 0, 1, divided by square root 2, tensored with itself. Okay, so 2 copies of this EPR pair. Okay, I know that this wasn't so enlightening, but I think that the fact that you can actually write down 9 4x4 matrices and just check that what are their eigenspaces and verify that no matter what state you start with, if you measure according to these eigenspaces, then the line player will always satisfy all the conditions. This is a nice thing that anyone here who wants to just check things, do some exercise and check by hand, it's a nice exercise and it works. Okay, great. So that was that. I think here I need the plus sign, but I'm not sure.
You need minus.
No,
you want
the product of the column needs to be 0. I think I need it that way. Yeah, I think this is the correct way.
Okay.
Okay. Anyway, this was the magic square game. And the point is that the magic square game is robust. So the magic square game is robust in the sense, again, that it means that if a strategy, okay, so let's take, you don't need to take a projective strategy, but let's take a projective strategy here for convince. If a projective strategy, and again, I can just write the strategy of the point player. I'm not caring now about the line pair. So if a projective strategy, how does a projective strategy looks like? Questions are of the form Aij, right? Just what appears in the Ij cell, and answers are plus minus 1. Right, these are the questions and answers. So there is Aij, and I'll write it that way, Aij plus 1 and Aij minus 1 for any I and j between 1 and 3. And you generate from them matrices Uij, which is just Aij plus 1 minus Aij. This is the projection on the eigenspace of 1, and this is the projection on the eigenspace of minus 1. So I just write it like that, and this is now a unitary. We did this trick when we analyzed the CHSH game. So if you take the UIJs are close to the XZI tensor XZI in the table after some isometry. And also the state is almost the EPR pair. So if you have some projective strategy and it wins with 1 minus epsilon, then actually you generate these UIJs and they are close to the matrices that appear here. And I must say for the group theorists that you just need to see that actually the group generated by these 4 cells is just D4 squared, the dihedral group, the Pauli group of 2 qubits. Right, Dorit? This is the 2-qubit Pauli group. You're muted.
I'm not following because I'm looking for a more lucid explanation of what you just... Sorry, I thought that it was... I doubt that anybody could follow this connection to EPR pairs. I'm not sure, but
which one?
Okay. Tai has a question.
The fact that the matrices multiply to the correct matrices, this is at least clear, right?
Yeah, no, but the connection to, I mean, the whole idea here somehow got a little bit obscured. So, sorry, I'm just looking for
the idea that there is some quantum strategy. No, that it's good. Dorit, maybe I don't want to move on if this is not clear. I want to talk about
well,
it.
So the way I know it is not by a point. That's why I didn't disturb. You were using sort of a point versus line, right? And
yeah, row or column versus specific input. Yeah.
Yeah, usually it's done by row versus column.
Yeah, you're correct. You're correct that it's lots of time it is used that way, but they are the same game. So winning one of them, like any strategy that wins one of them defines a strategy that wins the other.
Since both players do the same measurement on both sides according to if they need some square, then it's just the same.
Yeah, no, that's not what bothers me.
I think the basic point here is that we have a system of equations which are not solvable over a billion groups, but they are solvable with over the operators.
Fine, if you're happy with that, then that's fine.
Right, but I mean, if you have...
But something bothered Dorit. maybe let's try to understand what's.
Yeah, no, it's not that it bothers me. I was just looking. So what happens here is that there are two EPR states, right?
Yeah.
And somehow, so the point is that all operators in one column, in each of the columns, commute with each other.
Yes.
And also in the
So-
row.
And also in each row. So
Right.
basically, if Alice gets one column, she can give an answer to the values of each one of the operators.
Right. They are mutually.
They're
measured.
mutually commuting. And also Bob, if he gets a row, he can give an answer to all of those. Now,
Yeah.
why is that
And of course, you can give, if he doesn't need everything, he just needs 1 point, then it's also okay.
yes,
The
yes,
fact that
no, that's not
quantum
what
player can, if one needs to answer less, then he certainly can do it. And the fact that the classical players can't do it is still remains the same. Slightly lower.
I mean, if there is
Yeah.
a
Okay.
question
So
here is
your test,
why-
Dorit, is a bit harder than my test. This is the point, right?
No, that's not at all my point.
No.
That's not my point. The
No,
issue
it's not your point, but okay, sorry, it's not your point, but your game is easier than my game. Is harder than my game, right?
Yeah,
But
but I
my
think it's
strategy
conceptually easier to think about.
but my strategy solves both.
Yes, I guess. Okay, so if you're happy with just staying with operators, then that's fine. But somehow I think I at least am not completely clear what is the role of the EPR pairs here at all.
For them to be consistent. It's not written in the correct way, okay? So this is just one player's side, right? There is another copy of this thing. Okay, now I understand, maybe. Okay, I think I maybe understand what's the problem. There's another copy of this magic square living. Okay, so this is the point player. But the line player has the same picture. And this is acting on the Hilbert space of one player, and this is acting on the Hilbert space of the other. So the actual measurements are tensor products of things here, right? So
Maybe, Michael, maybe you can draw the A and the B, where the A and the B, no, sorry, upwards. The A and the B in the EPR tensor 2. Can you put indices of A and B close to the correct states?
Yeah, just
it's A.
Yes, exactly.
This is B, right?
Right. So the whole point is that the EPR state somehow makes them consistent no matter what they answer.
And this is because they use the exact same operators on both sides, right?
Right. So I'm not sure. Is that okay? Is that clear to everyone why it is always the same?
I don't think it's clear. It needs.
they're
some
measuring the same. If they're measuring the same operator on both sides, they get the same results. That's all.
Okay, let's check that.
Because it's an EPR state.
Yeah, it's important that it's an EPR state. But my point was that it is only important because of the consistency requirement.
Right.
If I just wanted them to output satisfying outputs for the equations, no matter what state that they would have taken, it would be okay. But then they won't be consistent, right? If I check the row against the column, they won't be consistent on the common cell if they don't use an EPR pair.
Right. Yeah. So for example, if you wanted to do that with 3 players, that is no longer clear how to do, right?
Because of all these monogamy things, right? I don't actually know all of that.
Yeah.
Yes. Okay. So this is, you say, a very 2-player-ish phenomenon.
It's a very specific thing to the EPR state that no matter how, in what operator you measure one side, if you measure in the same operator in the other side, you get the same answer. Okay.
Cool. Okay, so I still want to talk a bit about the group theoretic thing here. So my claim is that the robustness of this game can be achieved by stability of this group. Okay, so you just take these 4 operators, it generates. So I asked Dorit, what is the name you used? So this is the Pauli group on 2 qubits, right? So the stability theory of this group, finite groups are easily stable, but you need to say something about the constants of this stability to get robustness. So this comes from the work of Gowers and Khatami for higher powers of this dihedral group. But for the DF4 to the 2nd power, you can just calculate it by hand. You can see that so you can just get this result by hand. The fact that any almost perfect strategy needs to be close to these actual operators. So you can use some norm on operators, and actually you can even use the Hilbert-Schmidt norm in this case, and this is the norm where they are either close or far away.
This is like the solution group of this linear constraint system?
Exactly, this is the solution group. It's equivalent to asking what is the solution group.
Okay.
Okay, so this was the magic square. It was a bit of a detour to feel things about, I want to finish with a very important point. So if you weren't with me during the magic square, please be with me now. It's an important point. We will get back to it. And I think this is maybe the most important gadget tool. It's the hardest working tool in the MIP star is equal to RE result. And also this next thing is included in MIP star. And I call it the super Pauli basis test. And I call it that way.
Can I stop you just for a second about going backwards?
Yeah, great.
Just because I think it's a little bit confusing, the EPR, what is the role of entanglement here? There's sort of 2 places where it can hide. One is in this tensor product in each of these squares, right? X tensor I tensor X, etc.
Yeah, but it's not there.
This is not at all where it hides. It hides,
these are just 4x4 matrices.
Right. It's just a way to describe the 4x4 matrices, and as long as they satisfy the equations, that's fine. The reason why we need entanglement is because we need to somehow correlate between this square of matrices and the other square of matrices. And this is done by
2 classical players can always, if we are using your test, they can always answer a row correctly and answer a column correctly, but they cannot do it in a consistent way.
Mm-hmm.
And yeah, you're right. The way we use entanglement here is for them to be consistent on their answers. And somehow they can do it, which is the magic of the EPR pair. Okay. So now I want to talk about the super Pauli basis test. This is my name to a composition of several tests that appear in the MIP star is equal to RE and in the next piece contained in an MIP star result. And the reason that I'm showing it that way, Nati, I don't hear you if you talk to talking to me.
Is it just a question, or you seem to have an answer which you didn't tell us? Or am I wrong?
I'm sorry?
You see, my sense was that you're asking a question because you had a better answer, but I didn't understand.
I wasn't asking a question. I was trying to clarify something which wasn't, I felt, very clear. Where is the role of entanglement? And I think now is the way everybody was describing it together, it's clearer, maybe.
You had an alternative way to explain what entanglement was doing?
Well, I don't know if it's an alternative way. There's a hidden thing here, which I didn't feel was said very clearly, which is that if you have an EPR state or a maximally entangled state, here you have 2 EPR states, which are just a maximally entangled state, which can be written as superposition over I tensor I, where I goes from 1 to 4. a maximally entangled state has this amazing property, which goes beyond classical correlations, which is, so if you look at this state that I just described and you just measure it, then clearly you have complete correlations, full correlations. You measure I here, you measure also I there. But a maximally entangled state has this amazing property that no matter in what basis you measure in one of the tensor product spaces, you pick a basis, you pick the same basis, essentially. You measure something here, you measure exactly the same thing there. And this is a very simple property of a maximally entangled state, but this is what underlies this fact that actually you can have you can win this game with probability 1.
Okay, so I want to draw something that will maybe even like, we can see that if we use Dorit's definition of the game, that one player gets a row and the other player gets a column, they have a single cell that they need to agree on, right? In the row and the column that I draw, it's the I tensor X thing. But the way that they actually calculate what they need to answer is by measuring I tensor X, the row player on his side and the column player on his side. And since this is the exact same operator, they will get the same exact answer if they're using a maximally entangled state.
It's the exact same operator used to measure different particles, but they are fully correlated because of entanglement.
Okay. I will not be able to say everything that I wanted about the super Pauli basis test because we need to finish now. But I will say that this game enables us exactly to reduce questions, in the sense that somehow this game will enable us to send a point to one player and a subspace to the other, in such a way that the point player will not know what is the subspace, and the subspace player will not know what is the point. And this is the way we reduce things to polynomial. We will just use this super Pauli basis test. It will force the provers to generate a point and a subspace in a way that they don't know about each other's information. And then they
what you didn't mention, the point is on the line or on the subspace.
I did mention it.
Oh, sorry. So I didn't know.
Talked about this thing, but maybe now I didn't mention it. But
no,
the point is exactly that the point and the subspace are contained, like the point is in the subspace, but they still don't know about the one another. We need that the point. Okay, so in some sense, we need to uniformly choose a subspace, then uniformly choose a point in the subspace, send the subspace to the subspace player without saying what is the specific point that we chose, and send to the point player only the point that we chose. This is the way we need to distribute our questions, but these are exponentially long things. The point and the line or plane or three-dimensional space, all of them are exponentially long to describe. So we need some way of forcing the provers to measure these things by themselves. And this is the product of the super Pauli basis test. And I think now we have the tools to understand better what does this test do. Because when I talked about it at the end of my previous talk, I think it was very hand-wavy, and focused. I focused on how you would prove it instead of how do you use it. So now I'm going to elaborate more on how do we use it and where the magic square games gets inside and so on, and why the magic square game is in some sense a small version of the super Pauli basis test. And then we would finish the question reduction. And then we will be able to talk about PCPs and answer reduction, and you will help me to understand this part because this is more cryptic to me. Okay, we can see the discussion, but I think formally we are done.
Thank you.
Nati, did they answer this question that you had? Sure. In any basis, the answer on the left side is the same as the answer of the right side. So basically, if you have two provers, Alice and Bob, then no matter in what basis they want to measure or what operators they choose to measure, if they measure the same operator, they will get the same answer. So what happens in Michael's two squares is that Alice looks at her square, and she, for example, she got the request to measure, I don't know, this column. So she just measures all the operators in her column, which commute, so she can do that.
It's one
She
measurement.
measures, sorry?
I said
You can think of it as 3 consecutive measurements because they are all commuting, so you can do the measurement one after the other without interfering with their solution.
Yeah, which means that you can actually do them at the same time. It's one measurement.
Yeah, but okay. And I don't know, it's easier to think about it. Just measure one, then measure the other, then measure, and all of them, they're well defined. The eigenvalues of each of these 3 operators is well defined. And so she looks at her her particle, which is 4-dimension, two qubits, it doesn't matter. It's just 4-dimensional particle. And she measures all these 3 operators, and all of them have some definite eigenvalue. And the product is 1. And now Bob got some row, and he measures his operators in that row. He measures his particles, his part. And the point is that, well, his operator that he measured here has the same eigenvalue as this operator measured here. And this is the only place where you use entanglement. It's the fact that his value is the same as the value of Alice, even though they measured different particles. And even though they could have measured different operators, but still it's guaranteed, no matter in what basis, that their values will be the same because of entanglement.
Yeah, but I think at this point, this is just this is a technical issue. Now, the point is that you can play this game and there's just one strategy basically for the players to win. And there is another game also with one strategy for the players to win, in which one player needs to answer a point and the other player needs to answer a subspace.
Yeah, it's a bit more complicated, but we will force them somehow to do this.
Yeah, no, okay, fine. But there's another game so that in order to win that game, the players need to use their entanglement in order to choose a point and a subspace, while the first player knows the point but not the subspace, and the other knows the subspace but not the point, and yet the point happens to be on the subspace. And this way we can force the players to do this point versus plane test on themselves. They are actually choosing the questions from themselves, and that's why we don't need to send them the exponential sized questions.
Actually, you can define such a game right now. Take exponentially many magic square games. My claim that you can interpret, you can choose the rows and the lines in such a way that for them, in such a way for the many copies of the magic square game, in such a way that you can then force them to use some output of this game as the calculation of a point and a line, or a point and a subspace. The problem is that this is not robust. So already you can define such a game, as Guy said, that you can force the players to measure some qubits with an X measurement and some qubits with a Z measurement, and then interpolate, and then for the other, and so on. So you can do this kind of thing only using magic square games, but it will not be a robust self-test of this phenomenon. So we will need some robustness, and this is why we need a more complicated game. I will talk, like Guy just mentioned what we want. I don't know, I will talk heavily more about it next week, but we want some properties out of this game, and the magic square game has this property, but
yeah, but the main thing that Guy said is that somehow on top of this game, where here we have a referee that sends Alice and Bob the row and the column, somehow in the self-test, you actually design it so that Alice and Bob make their own choice of the measurements, right? Guy, this is what you wanted to say.
No. You need to tell them how to measure. Okay, so okay, it's a bit confusing. You're right that there is something that is a bit confusing here. My claim is that if you just want your pair of players to share many EPR pairs, exponentially many EPR pairs, and then force them to either measure with an X measurement on one of these EPR pairs or a Z measurement on this EPR pair, you can do it just by taking exponentially many magic square games and play them. Right? In the magic square game, there is this, you can force the players to measure an X measurement or a Z measurement on either of the qubits that they have. You just ask for the point player to do X tensor X if you want both coordinates to be measured by X, X tensor I if you want him to measure the left coordinate by X, but the right coordinate to do nothing. So you can, the magic square game has lots of, it has many, you can like enforce many measurements on the player by asking him or her to answer a row or a specific row or a specific line. So asking this column, for example, I'm not drawing anything, right? Now it's drawing. So the purple column that I marked before, if you ask him to measure according to this thing, okay, maybe it's better to talk about the point player. The point player is better because here I'm measuring both the left by X and the right by Z, right? Okay, so I'm forcing two things.
Michael, can I stop you for just a second, just so that people don't get completely confused? When you talk about exponentially many EPR pairs, this is actually the same as having just an exponential dimension Hilbert space in the state sum over II, where I go tensor here, where I goes from 0 to 2 to the n minus 1. So you have just a maximal entanglement between just a huge dimensional particle on one side and a huge dimensional particle on the other side.
Yeah, but I do want them to come in registers so that I can play the first magic square game with the first register and the second magic square game with the second register.
Right, but eventually you will want to do some things which are much more complicated than that.
Yeah, this is true. But I think you need even doubly exponential many, like I for 1 up to 2 to
yeah, you have doubly exponential, not exponential.
Yeah, so, but my claim is that if we just want to somehow force the players to measure X's and Z's on some of their qubits, you can just take a composition of magic square games. And we will see that the problem comes from the robustness requirement. So in the sense of self-testing, this is still a self-test. It's not a robust self-test, but it is a self-test. This was for those who were with us at the end.